Welcome to the Code Navigators. Before we chart our course through today's chapter, we do have to begin with our official legal disclaimer. This content is generated strictly for educational purposes only. It is not professional advice, nor is it a substitute for a professional consultation with a qualified professional engineer, architect, or code official. You, the listener, must always consult the official, current international building code and a qualified professional for any specific project or application. And we want to be explicit. We won't be reproducing or stating any copyrighted material in its original form, just discussing the concepts, requirements, and principles found within the code's text. All right, now that we've completed that essential regulatory checkpoint, let's talk about why we're here. Our mission is to guide you through the dense landscape of the International Code Council codebooks. We don't just summarize, we explain the contents of specific chapters and show you exactly how to navigate them effectively. This knowledge is crucial, whether you're studying for your ICC exams, preparing for a site inspection, or just trying to understand complex construction law. This show is built on a foundation of AI-assisted generation. But rest assured, the production and, most importantly, the technical oversight of all this material are conducted by a human code professional. We want to ensure we maintain absolute accuracy and clarity. Today, we're tackling one of the heaviest chapters, both literally and figuratively. IBC Chapter 22. Steel. Steel is the skeletal frame for so many modern structures, from skyscrapers to warehouses, and this chapter is where the International Building Code lays down the critical minimum requirements for how that structure must be designed, detailed, and built.
That's absolutely right. Our goal today is to go far beyond just reading the section titles. We are breaking down this essential chapter, focusing on the minimum requirements that govern the quality and performance of structural steel, composite construction, cold-formed steel, and even specialized items like steel joists and storage racks.
So if you've spent any time with the IBC, you know that some chapters, like, say, concrete or masonry, they might contain a huge chunk of the actual design methodology right there in the text. But Chapter 22, it works differently. It functions more like a sophisticated roadmap, doesn't it?
It does. It's probably the best example in the entire code of a central hub-like an index that organizes and directs the user to highly specific external technical standards. The IBC doesn't try to rewrite the American Institute of Steel Construction's 500-page specification. It just tells you precisely when and where you have to use it. If you're working with heavy structural steel, Chapter 22 immediately points you to AISC. If it's light-gauge cold-formed steel, you're sent over to the American Iron and Steel Institute, or AISI. And for open web members, the Steel Joist Institute SJI rules apply.
And that organization is really the key takeaway for you, the listener, especially if you're studying for an exam. You aren't expected to memorize every single design formula, but you absolutely must know which reference standard governs which specific steel system. That navigation skill is what's tested over and over again. So let's start with the basic rules, the foundational requirements that govern the material itself, regardless of whether it's a massive column or just a small cold-formed stud. Section 2201 gives us the general scope, covering quality, design, fabrication, and erection. But for anyone on a construction site, whether you're inspecting or building, Section 2202, identification of steel for structural purposes, is really where the rubber meets the road.
Identification is, it's fundamentally crucial. In modern construction, structural steel is a manufactured product. It's fabricated off-site, sometimes hundreds or even thousands of miles away. It shows up on site, maybe it's painted, maybe it's a little dirty, and you have to install it. How do you, the builder, the inspector, the design professional, how do you guarantee that the material that was just delivered has the specific yield strength, the ductility, the grade that the engineer specified?
And that's where the system of marks and paperwork becomes so essential. Steel isn't just steel. It's A992 or A36 or A500 grade B, and those are not interchangeable.
Exactly. Section 2202 is explicit about this. The identification of primary structural elements, whether it's standard structural steel or cold-formed members, it has to align with the specifications from standards like ASIS S100 and ASIS S240. And this is more than just a convenience. It is a critical link in the chain of quality control.
So we're talking about two components here, right? There's the physical marking on the steel itself and then the documentation that comes with it.
Yes, and honestly, the documentation is often the more critical piece of the two. The code requires identification marks to be visible, but it also, and this is key, it mandates the requirement for test records. These records, sometimes you'll hear them called mill certifications or material traceability reports. They are the steel's verification. They have to be furnished to the code official to prove conformity to the ordered grade, the specification, and all the provisions of the chapter.
I've seen scenarios where a piece of steel loses its identifying mark on site. Maybe it gets ground off during welding prep or it's damaged in shipping. If
Mm.
that mark is gone, what happens then?
Well, if the grade isn't readily identifiable from the markings, those test records become indispensable. I mean, without them, you have absolutely no way to verify that the actual material yield strength meets the design assumptions. If the design called for A992 steel, which has a nominal yield strength of 50 kc, but the delivered product is actually A36, which is 36 kc,
Oh,
the entire structural safety margin is instantly compromised. The inspector has the authority to reject that steel outright or require specific and often expensive testing before it can be used.
That really puts into perspective why Section 2202 is so foundational. You can't design safety into a structure if you don't even know what you built it out of.
And moving from identity to integrity, Section 2203 addresses the protection of steel. This is primarily about corrosion. Steel is incredibly robust, but its one true nemesis is rust, which, reduces the effective cross-sectional area over time.
So what are the specifics on that? Does every single steel member need to be painted or treated?
No, and that's a common misconception. The section is pretty clever. It distinguishes based on exposure. For general structural steel elements, your heavy beams and columns, the requirements for painting or treatment for elements exposed to weather or earth, they have to conform to specifications in AISC S100 and SJIJ 100. But if the steel is completely encased in concrete or, say, drywall in a controlled interior environment, often no protection is required because the environment itself is non-corrosive.
So if a steel beam is part of an exterior canopy, it definitely needs protection. But if it's a column hidden inside the conditioned space of a building, it often doesn't. That makes a lot of practical sense.
Correct. But then we have to look at cold-form steel. Cold-form steel light frame construction, think of your typical studs and tracks. It's inherently more vulnerable. And why is that? Because the material is usually much, much thinner. We're talking 18 gauge or even lighter. A tiny amount of corrosion represents a much larger percentage loss of the load-bearing cross-section.
That's fascinating. So a microscopic layer of rust on a massive W-section beam is pretty much negligible, but that exact same amount of rust on a thin, cold-form stud could potentially lead to failure.
Precisely. And for that reason, the protection requirements for cold-form steel light frame construction must adhere to AIC S240 as applicable. This usually means pre-galvanization, a zinc coating, to protect against corrosion, especially when it's used in moist or corrosive environments. It ensures that long-term integrity is maintained through the building's life.
So it's the code recognizing the inherent differences in material geometry and risk. Okay, so once we've identified the material and we've protected it, the next logical step is Section 2204, which covers how all these pieces are fastened together, connections.
And this is really where design meets workmanship. Section 2204 details the design, workmanship, and qualification requirements for everything: welding, bolting, and anchoring. It's basically the assembly manual for the entire structure.
And given that connections are statistically the most common point of failure in a structure if they're done improperly, I have to assume this is a hot spot for special inspection.
Oh, absolutely critical. The code references Section 1705.2 explicitly here, which mandates special inspection of welding and bolting. Special inspectors are certified professionals, and their job is to verify the procedures, the materials, and the final execution of these high-stress connections. This includes checking weld sizes, making sure the proper welding consumables are used, and most importantly, verifying high-strength bolt installation.
What's the major concern with high-strength bolts? Is it just about making sure they are tight enough?
It's actually more nuanced than just tight. High-strength bolts rely on achieving a specific tensile pretension, a clamping force, to transfer shear loads through friction, rather than relying on the bolt shank actually bearing against the wall of the hole. Section 1705.2 mandates specific installation methods, like turn of nut, twist-off bolts, or direct tension indicators, to make sure that the required minimum tension is achieved reliably. If a high-strength connection isn't properly tensioned, the joint can slip, and that can lead to instability or even failure.
So the special inspection isn't just a visual check at the end, it's about verifying a process.
Precisely. And let's not forget anchor rods. Section 2204.3 focuses specifically on these really critical connections between the steel structure and the concrete foundation. The code addresses both embedment and bearing here.
I remember the specific wording of that section. It says something like, anchor rod projections and threads must engage the through-connected material fully, and the threads of the bolts must not bear greater than the length of the threads on the bolts. Why that specific focus on the threads?
That detail is absolutely key to preventing a very specific and nasty failure mode. When a load is applied, you want the bearing to happen on the smooth shaft of the anchor rod, not on the threads. The threads are inherently weaker, and they're susceptible to stripping or localized failure under bearing stress. The code mandates that the anchor rod projection has to be adequate, so the nut fully engages the threads, and that the force is transferred reliably and safely into the foundation. It prevents inadequate embedment, which could lead to pull-out failure or shear failure caused by the threads bearing against the steel base plate.
So it's all about load transfer integrity. That ties together these foundational rules perfectly. Know what you have, protect it, and then connect it securely. All right, now we can transition from the general rules of material quality and connection integrity to the core systems that form the main structure of a building. We'll start with the behemoth, section 2205, structural steel.
This section covers the heavy lifting, the wide-flange columns, the beams, girders, and trusses that really define the skeleton of commercial, institutional, and high-rise construction. For all general structural steel applications, the code is very direct. Design, fabrication, and erection have to be in accordance with AISC 360, which is officially titled Specification for Structural Steel Buildings.
And AIC 360 is essentially the Bible of heavy steel design, right? It covers everything from design methodologies like load and resistance factor design, LRFD, and allowable stress design, ASD, to the specific requirements for different member types.
It standardizes the entire process. The IBC simply adopts it by reference, which ensures that every engineer is using the same baseline of performance and safety when they're designing these members. If you are designing a beam against bending, you have to use the equations and criteria set forth in AISC 360, period.
But this is where the complexity increases dramatically, isn't it? Seismic design. I mean, steel is naturally ductile, which is fantastic for handling earthquake forces, but the code demands specialized detailing depending on the risk level.
Absolutely. When you're designing for lateral forces, the structures have to comply with the provisions of ASCE 7, which is the minimum design loads for buildings and other structures. If a structure is assigned to seismic design category B or CISO, moderate seismic risk, it must be designed for specified seismic force resisting systems. These systems are typically detailed to ensure maximum ductility and energy dissipation during ground shaking.
Okay, but what if a designer wants to use a simple, ordinary steel system that isn't specifically detailed to be a highly ductile seismic system? Does the code even allow that in seismic zones?
It does, but with a significant constraint designed to mitigate the risk. This is where the response modification coefficient, or the torr factor, becomes the central focus. The true factor is a numerical value that represents the system's expected performance and ductility. Highly ductile systems, like special moment frames, they have a high draw value, often 8 or even higher, and that allows the designer to reduce the calculated seismic forces significantly because they know the system will absorb energy without collapsing.
And if they choose to use an ordinary non-specialized system?
The code imposes a heavy penalty. If you use a steel system not specifically detailed for seismic resistance, Section 2205 references, for instance, a cantilever column system used as part of the seismic force resisting system, you're forced to use an area value of 2, as detailed in ASC 7, Table 12.2-1.
And a value of 2 compared to, say, an 8 means the design seismic forces are 4 times higher. That's an enormous cost implication.
It is. It is the code's way of saying, if you're not going to design the system to yield gracefully and dissipate energy, the ductile way, then you must design it to resist the full force without yielding at all, which is the brittle way. A system designed with an R of 2 will require significantly larger, heavier, and more robust members, and that results in a much more expensive structure. It basically incentivizes the use of the specialized ductile systems that are detailed in the code.
It's a brilliant risk management tool. The code is using material cost as a lever to push designers towards safer, more resilient structural solutions in high-risk zones.
And that leads us logically to Section 2206, which covers composite structural steel and concrete. This is the integration of the two primary structural materials.
Right, composite construction. It leverages the best qualities of both materials. Steel takes the tension loads very efficiently, and the concrete slab, which is attached via shear connectors, takes the compression loads over the steel beam's top flange.
And to achieve that structural synergy, systems acting compositely have to comply with two major standards. This ensures a seamless integration. You have to comply with AISC 360 for the steel element, and critically, ACI 318, specifically Chapter 14, which governs the concrete aspect of these composite members.
So the code is making sure that the shear studs, which are essentially the bridge between the two materials, are designed correctly under the steel code, and the concrete surrounding those studs is detailed correctly under the concrete code.
Precisely. And in terms of seismic requirements for composite systems, the principle stays consistent with pure steel. Seismic design requires the use of the appropriate response modification coefficient, $3 in accordance with ASCE 7, Table 12.2-1. The R factor for a composite system will depend on its specific detailing and expected ductility, just like any other lateral force-resisting system.
Okay, moving on. Section 2207 covers steel joists. These are those lighter, open web members you see so frequently in large spans for commercial roofs and floors. They get great efficiency because of their truss-like nature.
Right, and steel joists and joist girders are governed by the Steel Joist Institute, or SJI, specifications. Because these are highly optimized, often proprietary products designed by the manufacturer, this section is maybe the most documentation-intensive part of Chapter 22. The code essentially shifts the liability and the engineering requirements to the joist manufacturer, but the registered design professional of record has to set the initial design criteria.
Okay, so let's unpack those documentation requirements because this seems like frequently tested information.
Yeah.
What does the registered design professional, the RDP, have to provide initially?
The RDP has to provide all the specific information regarding the steel joist and joist girder design requirements in accordance with the SJI specifications. This includes listing all applicable loads, specifying the end supports, and detailing the anchorage, bridging, and bridging termination connections required to resist uplift and lateral loads. Basically, the RDP sets all the boundary conditions.
So the RDP tells the manufacturer, here are the maximum loads, here's the temperature, here's the exposure, now you design the joist to meet it.
Exactly. Then the joist manufacturer takes that criteria and provides submittal documents demonstrating their product meets those requirements. And this is where the list of special loadings becomes absolutely critical.
When we talk about special loads, we aren't just talking about a uniform floor load, are we?
Not at all. The manufacturer's submittal documents have to detail a list of specific loads that must be considered in the design. These include concentrated loads. So think of a heavy piece of mechanical equipment resting on the joist uniform loads, non-uniform loads, net loads, and crucially, end moments and connection forces.
Why are non-uniform loads so relevant for joists?
It's because of how joists are constructed. Joists are essentially trusses, and the wet members, those diagonal pieces, are highly sensitive to the location of loads, known as panel points. If you have a big HVAC unit that applies a concentrated load halfway between panel points, that can induce severe bending in the cord members. That could potentially lead to a localized failure that a uniform load analysis would never even predict. The manufacturer needs to show they've accounted for all these irregularities.
That distinction is high-value knowledge. It really highlights why joist design is so specialized.
And furthermore, the submittals have to cover special considerations. Things like profiles for joist and joist girder configurations that differ from standard extended ends, like when a joist goes past a column line to support a building facade, and any non-standard live load deflection criteria. An extended end completely changes the moment diagram. It turns a simple span into a cantilever, which requires much heavier reinforcement at the support.
And beyond the design itself, the placement has to be documented.
Correct. Section 207.4 requires steel joist placement plans to be provided to the job site. This ensures the field installation matches the approved construction documents. And finally, Section 2207.5 reinforces the need for design calculations.
Can you elaborate on that calculation requirement without getting into the actual math, of course?
Certainly. The registered design professional has to submit calculations, including a cover letter, that demonstrate compliance with the SJI specifications. The manufacturer must also submit their calculations, including the joist placement plan, sealed and signed by the registered design professional. The essential takeaway here is that a complete, traceable, and sealed set of calculations demonstrating compliance for the joist and the supporting structure is a mandatory requirement for plan review and for permitting.
That covers the primary systems. Now let's move into structures that are a bit more niche, but are still highly regulated, starting with Section 2208, which covers steel cable structures.
These are less common, but they often involve very large public spaces or specialty structures. When you're dealing with the design, fabrication, and protective coatings of steel cables and related structures, think of suspension elements for stadium roofs, tension fabric structures, or even pedestrian bridges. The requirements have to be in accordance with ASTE 19. Again, the IBC is just acting as the authoritative index, deferring the technical complexity to the specialized standard.
Next up, Section 2209. Steel storage racks. Now, this seems simple on the surface, but if you've ever been inside a modern logistics center or a big box store, these racks are essentially multi-story, highly loaded structural systems in their own right.
Oh, they are massive dynamic structures, and their collapse can be catastrophic, which is why they're regulated. The general requirement mandates that the design and erection of steel storage racks, including pallet racks and stacker racks, must comply with the standard from the Rack Manufacturers Institute, our ME and SI MH 16.1.
And since these can be so tall and carry enormous weight, their seismic requirements must be extremely stringent.
They absolutely are. Seismic design has to comply with ASCE 7. And if these racks are assigned to seismic design category E or FSO, the highest risk zones like certain areas in California or Alaska, they must comply with Section 15.3 of ASCE 7. This is a special, rigorous section dedicated to non-building structures, ensuring that these tall, slender, heavily loaded systems can withstand dynamic forces without a critical failure.
Okay, now, let's talk about the certification requirements, which are based on complexity and height. This sounds like a very common exam question area. What are the thresholds for requiring professional certification?
The code sets two main triggers for required professional certification. First, if the racks exceed 8 feet in height, or second, if they are classified as a Type 4 storage rack.
And what defines a Type 4 rack versus, say, a Type 1 rack?
A Type 4 rack generally indicates a more complex system. It often incorporates automated storage and retrieval systems or custom, highly engineered features. So these specialized complex systems, or any rack over 8 feet tall, requires certification by a registered design professional. That means an engineer has to stamp the design and confirm the erection process adheres to the documents.
And what about the smaller, simpler racks?
For racks that are 8 feet or less in height, or for Type 1 storage racks, which are typically your standard, non-automated pallet racks, the certification shifts. These racks must be certified by the owner or the owner's authorized agent. They just have to provide a statement that the work was performed in accordance with approved construction documents. The code basically acknowledges that for simpler, lower-risk installations, the oversight can be managed internally, but that requirement for compliance with approved documents remains absolute.
That is a perfect distinction of how the code assigns risk based on height and complexity.
Now let's return to cold-formed steel in Section 22210, which encompasses the more general structural applications.
So this section would cover components like structural deck or maybe C-sections used as primary structural members, but perhaps not in a full light frame wall system. Is that right?
Correct. The design and construction of cold-formed structural members have to adhere to ACS 100, which covers the overall design specification, and ACS 310, which addresses the design of deck. The key challenge for cold-formed steel is always stability. It's thin, so it's vulnerable to local buckling and torsional instability, and the ASI standards provide the complex procedures needed to ensure stability under load.
And what about cold-formed floor and roof decks?
For non-composite floor and roof decks, they have to be designed and constructed in accordance with ASIS-RD 1.0. For composite decks, where the steel acts with concrete, they must comply with SDIC. These specialized standards ensure you get the correct strength and stiffness characteristics for diaphragm action and gravity load resistance.
How does the seismic design here integrate with that Predara factor concept we discussed earlier for heavy steel?
It's the exact same principle, just applied to cold-formed systems. Seismic design utilizes the response modification coefficient, $3, in accordance with ASE 7, Table 12.2-1. If the design uses specific highly ductile systems like moment frames or special moment frames, they have to be detailed in accordance with AICS 400. This ensures that the thin sections are detailed to prevent premature buckling failure when they're undergoing large displacements during an earthquake.
All right, and finally we get to Section 2211. Cold-formed steel light frame construction. This is an extremely common application, especially in mid-rise residential and multifamily construction.
It is, and this section governs the design and installation of that light frame construction, including all the members, connections, shear walls, strap brace walls, and diaphragms that resist lateral loads. This is where the engineering gets very granular. The primary standards referenced here are AIC S240 and S400.
Can you elaborate on the difference between AS240 and S400?
Sure. AIS 240 is the standard for the light frame construction itself. So, the rules for the geometry, spacing, and installation of the members. AIIS 400, on the other hand, is dedicated specifically to the detailing of seismic force-resisting systems. It provides the very specific requirements for connections and member restraints to ensure the lateral system, like a shear wall, can withstand seismic forces without a brittle failure.
The seismic requirements here must be paramount, especially given how popular these systems are in mid-rise construction.
For seismic force-resisting systems in cold-formed steel light frame construction, the R factor must be used in accordance with ASCE 7. And critically, if a structure is assigned to seismic design categories D through F, the seismic force-resisting system has to be designed and detailed in accordance with the enhanced requirements of AIC S400. This reflects the reality that in high-risk zones, even small details, like the spacing of screws on a shear wall panel, are absolutely critical to the system's performance.
Now, we need to spend a little time on probably the most valuable allowance in this section for residential builders, prescriptive framing. This is a game changer for speeding up compliance on smaller projects.
It is a critical allowance for sure. Prescriptive framing applies to detached 1- and 2-family dwellings and townhouses, provided they are 3 stories or less above grade. These specific low-rise residential structures are permitted to be constructed in accordance with ASCE 230, subject to certain limitations, of course.
So the designer can basically bypass the full complex engineering analysis required by S100 and S240 and instead use the simplified tables and rules provided in ASCE S230, is that correct?
That is precisely the benefit. ALEO S230 provides a simplified, prescriptive approach. It's like a cookbook of construction details that is heavily conservative, but it avoids the need for extensive calculations by a design professional for every individual member. This significantly streamlines the process for typical residential applications, provided they meet the height, occupancy, and geographic limitations. They're usually restricted in high wind or high seismic areas.
It's a pragmatic solution that balances speed and safety for high-volume, lower-risk construction.
And finally, within Section 2211, we have to address truss design. Cold-formed steel trusses are incredibly common in roof construction.
Trusses are complex assemblies where every single connection and member is critical. So what are the key regulatory points here?
Well, truss design requires very specific conformity to the AISI S202 standard. Design drawings have to conform to Section 11 of that standard, and critically, they must be provided to the job site. These drawings have to detail not only the truss geometry, but also the design of permanent individual truss members and the permanent restraint and bracing details needed to prevent long-term instability.
Why the focus on permanent restraint and bracing? I mean, isn't the truss inherently stable on its own?
Not entirely. Trusses are often designed using very slender compression members. If those compression members are not laterally restrained or braced, they can buckle out of plane long before they ever reach their design load. The manufacturer has to specify the necessary diagonal and lateral bracing required to maintain stability under service loads, and those details must be installed correctly in the field.
And since this is a complex, high-stress assembly, special inspection is mandatory, right, Dick?
It is. Section 1705.2 is referenced again, mandating special inspection for 2 items: permanent individual truss members and permanent individual truss restraint and bracing. And if the trusses span 60 feet or greater, the special inspection of these elements is explicitly triggered, which just underscores the code's concern about the stability of very long-span, slender compression members.
It really seems like the common thread throughout Chapter 22, from bolting to long-span trusses, is the emphasis on special inspection for any system that relies so heavily on precision in the field to achieve its design capacity.
That is the single most important principle of this entire chapter. The IBC shifts the rigorous technical requirements to industry standards, and then it uses mandatory special inspection to guarantee the compliance of those sophisticated details in the real world.
This exploration of Chapter 22 has given us tremendous insight into how structural integrity is managed in steel construction. To briefly recap, we covered the foundational requirements: identification, protection, and connections, emphasizing that non-negotiable need for test records and special inspection of critical connections, like welding and bolting.
We then charted the course through the major structural systems, heavy structural steel, where we learned about the mandatory compliance with AISC 360 and the critical role of the response modification coefficient, $3, in mitigating seismic risk by penalizing ordinary systems. We detailed steel joists, stressing the critical importance of manufacturers' submittals, including that lengthy list of special loads and the mandatory submission of design calculations.
And finally, we explored the specialized areas, including steel storage racks, where we detailed how certification requirements change based on height and system type Type 4 versus Type 1, and the two separate but related sections governing cold-formed steel and cold-formed steel light frame construction, noting that invaluable allowance for prescriptive framing, AIS 230, for typical three-story residential structures.
And if we connect all of this to the broader context of building regulation, Chapter 22 is just the perfect illustration of how the IBC functions as a regulatory system. It's not an all-encompassing textbook. Instead, it's a highly organized index that ensures consistency, technical rigor, and compliance by referencing these specialized industry-specific standards from AISC, AISI, and SJI. This genius system allows the code to remain current without having to be constantly rewritten every time a technical innovation occurs in the steel industry.
And that model raises an important final question for you, the code navigator. How does relying so heavily on external, constantly updated standards, like AICS 400 for seismic detailing, both simplify the overall structure of the International Building Code while simultaneously ensuring maximum technical rigor and flexibility in design? It creates a kind of symbiotic relationship that is just vital for modern, safe construction. We hope this guide has helped you navigate the extensive requirements for steel construction. Remember, if you find value in the Code Navigators and want to support the creation of future in-depth content just like this, please consider visiting the Patreon link provided in the show description. Your support keeps us mapping the code.
Thank you for joining us for this extensive exploration of the code. Until next time, keep building safely and keep those specialized specifications close at hand.